In this session, we shall deal with the conceptual part, rather the theoretical part of calculus from the beginning. The word calculus has been derived from the Greek word calcul. By the word calcul, they mean pebbles. Yes, pebbles. Such a word meant in that way is named for a subject, a famous subject like this. Why? Because in this subject, we'll be going to deal with very minute measurements. Very minute measurements. Let us consider some examples. We know that every body expands on heating. Suppose a circular copper plate is there and you heat it. Definitely it will be expanded. Yes, of course. Suppose the radius of the circular copper disc is 5 centimeters in the beginning. After heating it, can it be some 10 centimeters or 15 centimeters? No, it can be some 5.01 centimeters or at most 5.1 centimeters, that's all, which cannot be seen with your naked eye, of course. There are some practical instruments or ways of measuring it. And that branch of mathematics which deals with all such measurements is nothing but called calculus. See, a radius is increased by, say, some originally it is 5 centimeters and it expands to say 5.05 centimeters after heating. Then it affects in the measurement of the perimeter and the measurement of the area also. Corresponding to this change, how does that change, that is the area? Such type of discussions, such type of measurements are dealt with under the heading calculus. So far we could have noticed the very purpose of the subject calculus. Well, let us now enter into the practical part of this calculus. Under this heading, we first of all deal with the topic limits of functions. What is meant by limit? Limit of a function. Like that. Of course, there has been a brisk definition in textbooks which is available for us and which we could have got by heart, of course. What is the very purpose of introducing that one? What is the utility of that concept in our daily life? Such questions may arise. Let us deal with very few examples regarding the same. Suppose you have gone to a shop named Bata shop to purchase a pair of shoes. You have observed so many pairs. One pair has stolen your heart. It's very beautiful, it looks very beautiful and you liked it very much. There will be a price tag on that. It will be written 999 rupees 95 paisa. The price tag will be like this. You ask the shopkeeper, I like this pair very much, you pack it, I would like to get it, like that. He packed. How much do you pay? 1,000. What is the actual cost? 999 rupees 95 paise. How much should you receive back? 5 paise. Will he give? The shopkeeper, will he give you? Or do you demand? No, you just pay 1,000 rupees and enjoy a pair of shoes. What is the actual value used there? 1000 rupees. What is the exact value? 999 rupees 95 paisa. That's all. Yes. So in this occasion, the used value is just very little less than the more than the correct value. Correct value is 999.95 and the used value is 1000 rupees. And let me call the exact value of the exact cost of the pair of shoes as X. Is X 1000 or X approaches 1000? X approaches 1000. What is the exact value of X? 999 rupees 95 paisa. What is the approximate value or the nearest value or the used value? 1000. In such an occasion, we say that X approaches 1000 or X tends to 1000. By means of this example, we notice that if X tends to 1000, the occasion to say that X tends to 1000 occurs only when X is not exactly equal to 1000. It is very nearer to 1000. Such an occasion, then only you will say that X tends to 1000. Such circumstances in our usual mathematical life, in dealing with so many problems, X tends to 2, X tends to 0, X tends to 5, like that, so many problems we come across. What do you mean by X tends to 2? What is meant by X tends to 2? Of course, we write symbolically like this. X tends to 2 means X is not exactly equal to 2. Then, what is the exact value of X? It might be 1.999 or it can be 2.0001. Well, if the exact value of X is 1.999 and the used value is 2, then we say that X tends to 2 from left. Why should you say like that? On x-axis, the exact value of X lies to the left of 2, isn't it? The exact value of X lies to the left of 2 actually. And we are using X to be some 2. To be 2. That is, X tends to 2 from left. Why should you add that word from left? Actually, actual value of X is a value which is just to the left of 2. And X approaches 2. It is approximately equal to 2. That is why we say that X tends to 2 from left. In a similar case, if the exact value of X is 2.001 and we use the value X equal to 2 only, then we say that X tends to 2 from right. X tends to 2 from right. You observe the occasion. Even if X tends to 2 from left or X tends to 2 from right, the used value of X does not change. It is 2 only. At such a case, we say that limit of X is 2. From left or from right, it is 2. We have spoken of one variable, say X only, in this discussion. Now, let there be a function, say f of X is equal to X plus 1. Well, if what is f of 1, what is f of 2 actually? 2 plus 1 is 3. Now, X tends to 2, I am saying. What is the fate of f of X? X tends to 2, I am saying. What is the fate of f of X? X tends to 2 means X might be 1.999999. Then what is f of X? 1.999999 plus 1. 2.99999 approximately 3. So the left hand limit of f of x as x tends to 2 is the limit means the approaching value, the value to which it approaches, the left hand limit. As x is supposed to be 1.999 which lies to the left of 2, we say that the 2.9999 or the used value 3 is the left hand limit. Suppose x tends to 2 from right, then what is the exact value of 2? What is the exact value of x? 2.000001. Then what is f of x? What is f of x? 2.00001 plus 1, what is that? 3.0001. And in that case also the approximate value of f of x with the exact value is 3. And to express all these symbolically, x tends to 2 implies f of x tends to 3, we write. Combining these two, f of x tends to 3 as x tends to 2. F of x approaches 3 as x approaches 2. Limit of f of x is 3 as x tends to 2. This is of course the fundamental concept, which is in general we use with our daily life. But you see, mathematical definition is somewhat bulkier. Open intervals, modulus concept, etc., everything is there. Everything is there. Let us have a look over that concept also, and we spend a little amount of time to recall the definition. Believe that this is the real line. That is the line on which every real number can be expressed as a point. Of course, the real axis or x-axis. Let a variable x likes to tend to 2. Then it may lie either to the left of 2 or to the right of 2. Let us assume that a real variable x tends to 2. If it tends to 2 from the left, it is supposed to lie in a place to the left of 2. If it tends to 2 from right, it is supposed to stay. It is supposed to lie in a space very nearer to 2 to the right of 2. This part, the set of real numbers in this region is called a neighborhood of 2. Let me write this as 2 minus delta to 2 plus delta. This number is 2 minus something. This number is 2 plus something. 2 minus delta to 2 plus delta, where delta is a very small number. This is called a neighborhood of 2. Well, this is called a neighborhood of 2. Look here. X belongs to open interval 2 minus delta to 2 plus delta implies f of x belongs to L minus epsilon to L plus epsilon is C. L minus epsilon to L plus epsilon C. If it is possible to have a step of this form where epsilon and delta are very, very small positive real numbers, then we say that f of x tends to L as x tends to 2. X tends to 2 means x is supposed to lie very, very, very close to 2. Either to the left of 2 or to the right of 2. It is in the place surrounding to 2. That is in the neighborhood of 2. with a similar concept, f of x lies in L minus epsilon to L plus epsilon. What does it mean? It is supposed to lie in the neighborhood around L, that is in the place very close to L. Yes, suppose let me now have a pictorial explanation in view of diagrams which we generally use in our 10th class. A, B. This is number 2. All real numbers in 2 minus delta to 2 plus delta. This is L. If this x lies here, f of x lies here. If x observe this diagram. If a point x is considered here, where does f of x lie? Nobody knows. It can be here. For this, here. For all the points in this neighborhood, 2 minus delta to 2 plus delta, f of x will lie definitely in this neighborhood only. That is the relation between these two. If you decrease the size of this neighborhood, correspondingly the size of the neighborhood will be decreased here. So corresponding to every neighborhood here, corresponding to every neighborhood around L, a neighborhood around 2 will exist. This is the pure theoretical part around the limit. And this is explained in a brief sentence. Corresponding to every neighborhood around L, there exists a neighborhood around 2 such that for all the points in this neighborhood, images will lie here. Of course, this can again be expressed like this: mod x minus 2 less than delta. This can be explained mod f of x minus L less than epsilon. And I am sure very few occasions we may come across to use this definition. It is just enough to notice that definition, that's all. Let us put a full stop to this definition. This is the main concept. Yes, it is a sin if you do not consult with that. For that purpose only, I have considered this. This is the limit of a function. As we discussed earlier, at very few occasions only we are supposed to use that conceptual way of defining a limit. And the applications of that definition in the practical purposes, we shall now discuss with that. Moreover, if x tends to 2 from left, then we represent like this. You're not supposed to read it as x tends to 2 minus. No, it is not the correct way. X tends to 2 from left. Just like that, x tends to 3 from right. What does it mean? The exact value actually lies to the right of 3. That is, it may be 3.001 or 3.0011 like that. What is its limit? That is approximate value or nearer value or the approaching value. Its limit is 3. Of course, the right hand limit is 3. Here, left hand limit is 2. Okay, x is a real number, a real variable. Basing on that, a function f of x is defined. Then limit as x tends to 2 from left of f of x, limit as x tends to 3 from right of f of x. Like that we use the symbolism. Suppose f of x is equal to x plus 3. X tends to 2 from left, do you imagine? Then what is the exact value here? X tends to 2 from left means exact value is 1.99999, total is 4.9999, approximate value is 5. Therefore, limit of f of x as x tends to 2 plus 3, 5. Why? If it tends to 2 from left, it is 4.999. If it tends to 2 from right, then it is 5.0001. Wherever it is, whatever it is, the actual limit is 5. The approximate value or the nearing value is 5. So, this we mean left hand limit. This we mean right hand limit. And there are so many ways to represent these left hand limit and right hand limit also. Left hand limit at A. Limit as extends to A from left of f of x. Limit as extends to A from left of f of x. Limit as h tends to 0 of f of A minus h. F of A from left. All these are the ways to represent the left hand limit of a function when x tends to A from left. Okay, this we could have understood, A from left. This also we could have understood, A from left. What is this f of A minus h? What is this h concept? It's very simple. Look at this. Suppose this is A. X tends to A from left means where does x lie? Here. Every real number which lies behind A or to the left of A can be expressed in the form A minus h. So x is in the form A minus h. But we like to write x tends to A. That is A minus h tends to A. That is minus h tends to 0 or h tends to 0. Therefore, the left hand limit can be expressed as limit as h tends to 0 f of A minus h. And for the brief concept, for the brief expression, we use this. Accordingly, the right hand limit or RHL is this. Automatically, for a function, both left hand limit and right hand limit must be equal to say that it exists. That is, f of A from left is equal to f of A from right. Then only we say that the function f, the limit of f of x as x tends to A exists, or otherwise simply not. Well, let us have a conclusion. Limit as x tends to A of f of x is equal to L if and only if limit as x tends to A from left of f of x and limit as x tends to A from right of f of x exist, and limit as x tends to A is equal to L is equal to limit as x tends to A from right. Both of them should exist and they must be equal. Then only we say that limit of f of x as x tends to A is L. Now look at some standard limits. Right. Among these standard limits, the very first one is limit as x tends to A of x power n minus A power n by x minus A is equal to n into A power n minus 1. One of the most famous and useful limits, standard limits it is. Its proof is studied in our earlier classes itself. Such a standard limit it is. And let us observe some illustrations for this. Limit as x tends to 2, x to the power of 5 minus 32 by x minus 2. Imagine x power 5, what is 32? 2 power 5. So in the place of n, we have 5. In the place of a, we have 2. 5 minus 1. What is 5 minus 1? 4. 2 power 4 is 16. 5 16s are 80. So this is the very first standard limit. And there are so many applications for this. limit as extends to 1 of x power n minus 1 by x minus 1. Come on, what will be the answer? In the place of a we are having 1. 1 power anything is 1. Though only n will occur. So limit as extends to 1 x power n minus 1 by x minus 1 is just n. Well, let us observe some more applications of these two limits. Good. Limit as extends to a. It can directly be simplified, of course, by dividing both numerator and denominator with x minus a. If you divide it with x minus a, what will be the fate of numerator? M into a power m minus 1, and here n into a power n minus 1. As a result, we have m by n into a power m minus n. M by n into a power m minus n. Limit as extends to 2 x to the power of 10 minus 1024 by x to the power of 5 minus 32. Can you get this? In the place of m we have, what is 1024? It is 2 power 10. What is 32? It is 2 power 5. In the place of m we have 10 by 5 into 2 power 10 minus 5. What is 10 by 5? 2. 10 minus 5. 5. 2 power 5. 32. 32 2s are 64 is the right answer. And one more application of this is limit as extends to 1 x to the power of m minus 1 by x to the power of n minus 1. What is that? Just m by n. What lies here? In the place of here we have 1. So 1 power anything is again 1. Hence only m by n will occur here. Hence limit as extends to 1 of x power m minus 1 by x power n minus 1 is just m by n. Well, now you tell me the value of limit as extends to 1 of 4th root of x minus 1 by 5th root of x minus 1. Is it 4 by 5 or 5 by 4? In the place of m we have 1 by 4, in the place of n we have 1 by 5, hence the answer is m by n, that is 1 by 4 by 1 by 5. It is just nothing but 5 by 4. It is 5 by 4. Like that. These are the applications of the very first fundamental formula, x power n minus a power n by x minus a is n into a power n minus 1. The next formula, limit as extends to 0 a power x minus 1 by x is log a to the base e. And its proof can easily be observed in the earlier classes itself. Limit as extends to 0 of a power x minus 1 by x is log a to the base e. And similarly, limit as extends to 0 a power x minus b power x by x can be taken as, come on, can you guess? Minus 1 you can offer a power x minus 1 minus b power x minus 1 by x by x. So it is log a minus log b or log a by b to the base e. Just like that, limit as extends to 0 a power x minus 1 by b power x minus 1 is equal to, you just offer an x for both numerator and denominator by x, a power x minus 1 by x, b power x minus 1 by x, so that the numerator becomes log a to the base e, and for the denominator it becomes log b to the base e. So it is log a to the base e by log b to the base e is just nothing but log a to the base b also you can have. You can have. As by basing on that, limit as extends to 0 a power x minus b power x by c power x minus d power x. Of course, all a, b, c, d are all positive. How can you guess that? For numerator it is log a minus log b. For denominator it is log c minus log d. Those log a by b by log c by d. And you can get it simplified as you require according to the options given in the question related. Yes. So the answer is log a minus log b by log c minus log d. Now and then you can be observing problems like this also. Limit as x tends to 0, a power 3x minus b power 4x by x. Come on, what is the fate of that problem? A power 3x, we can have a cube whole power x. So it is log a cube minus log b power 4. That is 3 log a minus 4 log b. You can have the answer. According to the situation, you can change the question according to the convenience. Well, one more thing. Limit as x tends to 0, e power x minus 1. In the place of a, we have e. What is the answer? Log e to the base c. How much? 1. Answer is 1. So, for all this, this is of course the basic formula. Even though it has been derived, this is also a basic formula. E power x minus 1 by x is equal to 1 is also a standard formula. Let us observe the applications of that formula now. What is about it? You multiply with m, but both numerator and denominator. And here also. Limit as mx tends to 0, e power mx minus 1 by mx is 1 into extra m. So the answer is m. Just like that, limit as x tends to 0, e power mx minus 1 by nx. What will be the answer? It is just nothing but m by n. So far, we did not come across any limits involving trigonometric functions. Still, there are some functions without using trigonometric functions. Limit as x tends to 0, 1 plus x whole power 1 by x is equal to g is equal to limit as x tends to infinity 1 plus 1 by x whole to the power of x. Both are same. That is 1 plus 0 whole power infinity form. This is. What is g actually? Yes, what is g? The so-called exponent, which is generally used as a base for the exponential function e power x. From the view of this definition, only that e has been created. In mathematical analysis, in mathematical real analysis, actually, in the study of sequences and convergence, the number e has been named like that as the limit of this. Of course, in sequences, if n is a natural number, then limit as n tends to infinity 1 plus 1 by n whole to the power of n is also e. Actually, the sequence 1 plus 1 by n converges to one finite limit lying between 2 and 3. It is of course 2.718 and so on, etc. It is named as g. 1 plus 1 by n whole power n. Converges means tends to a. This is the conceptual definition of e actually. Basing on this, these things are created. That is also a beautiful concept regarding e. One more. Limit as x tends to 0, log of 1 plus x by x. How much it will be? It can be taken as limit as x tends to 0, log of 1 plus x whole to the power of 1 by x. You observe, 1 plus x whole power 1 by x as x tends to 0 is e, and log e to the base e is of course 1. So in so many calculations and in so many numerical problems we come across to use this formula, limit as x tends to 0, 1 plus x whole power 1 by x is of course e, and here it is log e to the base e is again 1. Looking at the trigonometric involvement, the very first one, limit as x tends to 0 of sin x by x is equal to 1 is equal to limit as x tends to 0 of tan x by x. When x is measured in radians only. Yes, of course, you have written sin x means sine of x radians only. If at all it is measured in degrees, it will be expressed like that, sine of x degrees like that. Yes. So you are supposed to use the formula when and only when x is measured in radians. If I ask you to calculate limit as x tends to 0 sine x degrees by x, is it 1? No. X degrees means you may have to convert it in terms of radians, so that it is limit as x tends to 0 sine of x pi by 180 by x pi by 180 into pi by 180. I think you might have understood what I could have written here. X degrees means x pi by 180 radians. Here it is only x. To use the formula, I have written x pi by 180. To get it cancelled, I have taken pi by 180. Of course, multiply this with pi by 180. This part is of course 1. 1 into pi by 180 is pi by 180. Likewise, like that, if at all a problem is given in terms of degrees, you must convert them into radians only in order to use these simple formulas, standard formulas. Like that, there are so many standard formulas are also there involving trigonometric functions.